welcome back to our next session, which is on compound interest. So to define, compound interest is the interest calculated on the sum of the principal and the interest after certain intervals of time, and I'll explain what this means later. The intervals of time are called the compounding periods, and this is important to note because it'll be used later on in our session. So here I've shown you an example of compound interest versus simple interest for a period of 2 or 3 years. The principal here, as you can see, is $1,000, and the interest rate I've given here is 10%. So for simple interest, you can see that it represents a linear growth because at the beginning of year one, you have $1,000 in the bank. Beginning of year two, you have $1,100 in the bank, and at the beginning of year three, you have $1,200 in the bank. You can see that this pattern changes for compound interest because at the beginning of year three, you can see that there's $1,210. So the question is, why? Well, for simple interest, you'll recall that the interest was calculated solely on the principal, which means that for every single year, the interest was calculated by doing 10% multiplied by $1,000, the interest multiplied by the principal. However, for compound interest, the interest is based upon the amount of money you have in the bank during the compounding period. So let's look at the example here. The principal here is $1,000. So at the beginning of year one, which is at the first compounding period, you have 10% multiplied by $1,000, which gives you $1,100. However, to calculate the interest for year two, you have to multiply 10% by $1,100, which means that when graphed, the interest will represent an exponential curve. So let's go back to our PowerPoint here. Let's look at the formula for compound interest. So as you can see, the formula here is A equals P bracket 1 plus I close bracket to the power of n, where A is the amount at the end of the time for the investment or loan, P is the principal invested, I is the interest rate per compounding period, and n is the number of compound periods. It's important to note that this formula right here is derived using the formula for geometric sequence, which is Tn equals AR to the power of n. And we'll explain in our next video how it's derived. So let's move on. Go back to our thing there. So let's look at an example. Whoops, wrong thing. Let's look at an example. So Mary wants to invest $5,000 from her job to save money for a new car. So that gives you the principal amount that she invested. Let's write that down. So the principal amount equals $5,000. If she just turned 16 years old, how much money would she have by the time she turns 18 years old if she invests at an interest rate of 5.3% per annum, compounded monthly? So that we can also get the time from that question. So she just turned 16. How much money would she have by the time she turned 18? So by that you can see that 2 years have passed. 2 years. At an interest rate of 5.3% per annum compounded monthly. So interest rate is equal to 5.3% per annum. However, this question says that the interest rate is compounded monthly, which means that at the end of every month, you have to take the amount of money in Mary's bank account and compound that amount, which means that we have the interest rate here given for every year, which means we have to convert that to the interest rate for every month. So let's just do that. 5.3% divided by 12, which would equal 0.44%. However, this isn't a very precise method, so we'll scratch that out and just leave it as 5.3% over 12. That's our interest rate, 5.3% divided by 12. So, and we have our formula, which is A is equal to principal multiplied by 1 plus interest rate to the power of n. So the principal we have here is $5,000. $5,000. 1 plus, and the interest rate we already said was 5.3% divided by 12. Just move that over. 5.3% divided by 12. And n, as we already mentioned, is the number of compounding periods. However, for this example, we can see that the interest rate is compounded monthly, but the period given to us is yearly. So we can see that the interest rate is compounded monthly, but we're given the time in years, which is 2 years. So we have to change the compounding period to match the compounding period. We have to change years to months. And we can do that by multiplying by 12. So 2 years multiplied by 12 months. So let's simplify that formula. Equals $5,000 brackets 1 plus 0.053, change it to decimals, over 12 multiplied by, to the power of 24. So let's just input that into our calculator. Bring that up. So you have 1.0, oh sorry, let me just do that again. So you have 0.053 divided by 12 equals that, plus 1. And you can see here the importance of keeping things as precise values, not just as rounded decimals. To the power of 24, which is equal to that, and multiply that by 5,000. At this point, it's okay to round because you have the final value. Equals $5, bring that up again, 5557.81. 5557.81. Value? Yep. So there you have it. By the time she turns 18 years old, Mary will have $5,557.81. Let's just check that with the answer. That's the question, and there we have it, the answer. We were correct. So let's just do another example here. Or rather, let's do a real life application of this scenario. So in Canada, we have savings bonds known as Canada Savings Bonds. And these bonds are available with options of both compound and simple interest. So the thing we want to find here is which is better. Which would you want to go for? So Canada Savings Bonds, just a brief summary, they run for a period of 10 years and they're usually available in denominations of $300, $500, $1,000, $5,000, and $10,000. Simple interest bonds, the bonds that are have an interest rate that's calculated based on simple interest. The interest rate is paid to you periodically, which means that every year or every month, based on the period, you get a certain amount of money emailed to you or paid to you. The Canada Savings Bonds that's compounded annually is not paid to you in certain periods. You get it all as a lump sum of money at the end of 10 years. So let's look at another example. For a certain year, the simple interest for Canada Savings Bonds was 7.9%. So let's just write that down. So simple interest rate is equal to 7.99%. And the compound interest rate was 7.9% also, except compounded annually. So compound interest, 7.9% per year. Both bonds are invested for a period of 10 years. So there we have it, T equals 10 years. Which option, 10 years. Which option gives the greatest yield if $10,000 worth of bonds was purchased? So our principal amount is $10,000. So they're asking us which type of bond would you go for to get which would give you the greatest amount of money at the end of 10 years. So let's calculate that for simple interest first. So actually let's do compound interest first. It's more interesting, plus it's also our topic. So for compound interest, we know that the formula here is amount is equal to principal multiplied by 1 plus interest rate to the power of the number of compounding periods. We know that our principal is $10,000. 10,000. 1 plus, and our interest rate is 7.9% per year. And we don't need to do any calculations for this because it's compounded annually and it's per year. So no need for any changes. And 0.79, change that to decimals. And it's for a period of 10 years, so 10 compounding periods. And if we calculate that, we get that over. So we have 1.079 to the power of 10, which is equal to that much, multiplied by 10,000, which is equal to $21,390.18. Just write that down. Equals 21,390.18. So that's how much we get if we bought the bonds at a compound interest rate. Now let's look at it for a simple interest rate. So the formula for simple interest, as covered in our previous video, was A amount is equal to principal plus principal times rate times time. So if we plug in our values for that, we get principal is $10,000 plus 1,000 times 0.079, change that to decimals, multiplied by 10 years. And if we simplify that, we get, clear your calculator, so we have 10,000 multiplied by 0.079, whoops, let's bring decimals, so 10,000 times 0.079 times 10. Oops, something's wrong with this calculator. Let's do that again. 10,000 times 0.079 times 10, which is equal to 7,900. So if we add that to the principal, we get $17,900. So as we can see here, the compound interest rate is way larger than the simple interest rate. Almost $3,000 difference, $3,490 difference to be exact. So to answer the question, they asked which interest rate would be better. So in terms of money at the end, compound interest rates would be better. So the question here is, why would anyone want to buy simple interest rate bonds? So if you recall, simple interest rate Canada savings bonds are paid periodically at the end of every year or every month, while compound interest rates are paid only at the end of the 10 years, the period of 10 years. So someone who would want the money at the end of every year would rather go for the simple interest bond, while someone who's willing to wait and who doesn't need the money right away would probably go for a compound interest savings bond. So there's our application. Now let's look at a counter example, a way to use this incorrectly. Let's move that over, new screen. So here we have a counter example. So let's say that John invests $10,000 in an RRSP that is compounded with an interest rate of 6% semi-annually. And the question is asking us to calculate the amount after 9 years. So let's write down our givens here. So John invests $10,000. So that's our principal amount. P equals 10,000 in an RRSP that is compounded with an interest rate of 6% semi-annually. So interest rate, that's supposed to be an I, is equal to 6% per semi-annually, so per half year. Or 6 months, same thing. And they're asking us to calculate the amount after 9 years. So that would be T, the time, compounding periods, or we should make that N rather. N, just fix that. N is equal to 9 years. So remember, this is a counterexample, so it's a way of doing it incorrectly. And as you can see here, this is done incorrectly because the N value, the number of compounding periods, should not be 9. Because look at here, it says 9 years, but it's compounded for every half year, semi-annually, which means that the number of actual compounding periods would be 9, so this is wrong. The number of compounding periods should be 9 years times 2, because semi-annually. So the number of compounding periods would be 18. So let's just whip up our handy-dandy formula here. Just amount is equal to principal times 1 plus interest rate to the power of n, the number of compounding periods. And if we input our values, we get the principal is $10,000 multiplied by 1 plus 0.06 to the power of 18. Now, kudos to the person who can figure out why this solution is also wrong. That's right, this solution is also wrong. This is not the correct way to do it. The reason is the I value. See here, 6% for every half year. Now, you should know that interest rates are always given on a yearly, relative to years, which means that this is actually 6% per year. So we need to change that to every half a year. Let's just move that over. So move that over here. We need to change 6% per year to 6%. How much would 6% be every half year, which would be 3%. So if we input that into our formula, we get amount is equal to principal, which is $10,000, multiplied by 1 plus 0.03, which is the interest rate, multiplied by, to the power of 18. So if we whip up our calculator again, we get 1.03 to the power of 18 is equal to that. And if we multiply that by 10,000, we get that amount equals $17,024.33. So that's the amount that John would have after 9 years. And as you can see, these are common, very common mistakes that students often make, which is not accounting for the compounding period and not changing the interest rate so that it accounts for the compounding period as well. So keep in mind these two common mistakes and you should have smooth sailing for the rest of your compound interest calculations. See you next time in our next video about compound interest versus exponential growth.